Hi my friends, today we continue to study the design accelerator presented in this ribbon. As you know from the previous tutorial, you gain access to the design accelerator by starting from an IAM template and then activating this tab, design. Today we try to create a disk cam which has a principal sketch here. You can see the future cam, also the oscillating follower, the plunger and the spring. The cam will have a certain shape, not a circle like here, and when it rotates, the oscillating follower is rotating about this axis and the plunger move up and down. The spring has the role to keep pressed the roll on the cam. Well, let's create this mechanism. You have to note that we have all the elements excepting the cam, which is to be designed. If you want to create it too, you have to download the components by using the indication in the description of this tutorial. Standard IAM, place. The first is the grounded object, which is the support. This is. Then we continue with the other. Oscillating follower, ESC, space. Plunger guide, ESC, space. Plunger, ESC, space. Roll, 2 instances. Shaft cam 1, shaft follower 1, and studs 2. Good. Now we apply constraints. Insert this face into this hole. Apply. This face into this hole. Apply. The bottom hole of the follower on this face. Apply. Now I place in a good position this to place the studs. Let me move them around the follower to have minimum of movements. Constrain, insert aligned this face into this hole. Apply. This face into this plane. Apply. Now opposite. This is to be placed here, and the other where is here is. Apply to be here. Okay, F6. I place them in a relative final position. Now we constrain the guide to be in the channel. Apply, and with the lower face to the right side of the channel. Here. Apply. You see the small hole here is down. Any face, because this is perfect symmetrical, on the face and the side on any side. Apply. Cancel. F6. Now, as you can see, we can move the guide and we can move also the plunger. Let's apply a constraint, tangent constraint between the roll and the slot in the plunger. Okay. Now, as you can see, we don't have a certain position for the guide, and we have to create it. The position depends of the position of plunger, and it depends of the cam. We have to create a circle here, which is the future cam, and to constrain the roll to that circle. To do this, you know the procedure, but I want to be sure. You have to use create component, create in place. In an assembly, we create a part. We select the appropriate template. We give a name, cam preliminary, okay, and we have to select a face to create a sketch, to create a part. The face is this, yes, because here we have to be placed the cam. Start sketch. The plane is the plane aligned with that, which is this one. We project geometry, this circle, and we create a new circle with a diameter of 90. This is the minimum diameter of the cam. Finish sketch. Finish part. This is the part, a simple circle. And now, since this is a very uncertain position, yes, we apply the constraint tangent between the roll and the circle. Apply. You see, we have a contact there. I cannot rotate the oscillating follower, but now, and this is not possible to be moved, and now we have to choose a position for the guide. I tell you, because this is well prepared, that that position is when they are aligned here. So constrain flush this face with this face. Okay. Once we finished with the positioning of the guide, we can renounce to this, or we just delete the circle which helped us to fix that position. Yes. Okay, I want to tell you that this minimum diameter in fact is the medium diameter. I change here and I'll change the front page, medium diameter, because you'll see we have another minimum diameter. It was wrong here. And now we move on to the design accelerator. Yes, design disc cam, not linear cam, not cylindrical cam, and we'll activate this by keeping pressed the key control to start from scratch, from the producer basic situation. This is with 25 here. We place our own data. The cam will be here. We start by selecting the cylindrical face and the frontal face. Yes, and we place our dimensions. 38 is the basic radius, and then we know the cam will have 10 millimeters width. The roller radius is also 10. The roller width is also 10, and the eccentricity is 10. Where is that eccentricity? It is here. You see, this is not on the line with the cam. It is up 10 millimeters, around 10 millimeters. Good. We want to apply 13 millimeters at the other end of the movement. Our result is here. So, as we know that this is 90 and this is 200, we'll multiply with 90 and divide with 200 the value of 13, which is intended for us to be here, and the value H maximum must be on the cam. Yes, that's all. We select the default function, harmonic, sinusoidal, and this is the graphic of the lift. How much lifts the roller together with the cam hump. Calculate. If nothing is read here, the result is good. You see in the calculation all the results and some input data. For instance, 5 newtons on roller. This means that the spring generates a force multiplied by 90 divided by 200, of course. Let's see how the cam looks. Okay, naming moment, and okay, this is the cam. When we eliminated the circle, there is no constraint for this. Let's add our constraint. Which one? Tangent. Constraint, tangent between the roller and the cam. Okay. Now, when we rotate the cam, you see there is only one movement of the plunger, but this is without a hole inside. Yes? Let's manufacture the cam. Double click on this new component in the browser. We select the face, we close the selection, and we have a center. We apply there a hole of 12.5, which is the diameter of the shaft, through all the part, the cam, not all the assembly. Okay, now we make another modification because we want to have a nice cam. We apply offset of 2 to both outlines, 2 millimeters, and then we apply extrude, cut 1 millimeter. Okay, the general aspect of gun metal, this and other 2 faces, only on this side is enough to be titanium polished. Good. Finish editing the part, and the situation is more interesting. Yes? Constrain angle of this kind between the plane, this plane of the cam, and this plane from the support to be 0. Okay, now we have the possibility to apply drive with a value of 360 and to see how this mechanism works. You see the movement here. Here is 13, and this level is a smaller value. Now we think that we want to have 2 humps. Yes, 2 protrusions, not only one, on this cam, to have on one rotation a double movement here, not only one. To do this, we can edit the disk cam, but using design accelerator. Very important. We can now study better this graph. This curve is the lift, and we have the other speed, which is this one. This is the acceleration. Yes? Good. Let's add what I said, a new hump. To do this, I make a smaller angle here, and now by selecting this, I apply add after to add a linear moment, and then I add here a random value of 5 millimeters for the next segment. Yes, this is the first and this is the other. We see red here now. Oh, what is this. In calculation, we have the result. CAM profile is undercut. What means this? Let's see. OK, accept, and you see here something very nasty. Also, the offset has disappeared because of this undercut. Oh, let's make some modification. I move this end to the right and the other to the right. Now you see there is no undercut. Why? Because these are more enlarged curves. Okay, you see, this is the new situation. Let's see that there are two movements here at one rotation. Drive, action, one, no, now is at 336, and we start now the movement. One, and the second is very slow. This is slow, and the next is rapid. Yes, during the 360 degrees. You can make any changes. You can place many humps on the contour. It's at your will. Well, but we want to apply a spring here. Yes, to have that force of 5 newtons as it was really applied. Yes, but no spring we have here. That is a force in the roller here without any spring. But we want to place here a spring with 5 newtons force. The force can be also modeled here by clicking here, and you see the blue contour with the force. Here is the last one is 5. Yes, do not forget, you can save all the data. Look here, I click here, I select a file, a name, and I open this file. You have here all the data and the force. Okay, we finished with this chapter. The spring must accommodate in this space. Yes, let's measure the space, considering this a maximum position. If not, let me find the maximum position by suppressing this constraint and taking a good view. Yes, this is the maximum position up, and this is minimum. Yes, the distances are M from this line to this face is 78 escape, and in the minimum distance the measure is 64. 78, 64. Keep in your mind. Good. To create spring, we use design accelerator. Here is the category spring, and we select compression, not extension, not Belleville, not torsion. Keep Control pressed to use the initial data or default data. We select positions, yes. The axis is the axis of this small hole. The start plane is this, and now there is a presentation, a preview of a large spring. Why? Because the wire diameter is 7 millimeters. We want to place 1.2 millimeters. Yes, this kind of wire. And we place here from 78, let's say 82 is loose spring length, the spring without any load. Yes, we have here a good presentation or preview. This is the loose spring length, L0. This is loaded, contact and loaded, and this is maximum working value, and then totally compressed. We choose this value. Number of active coils, say 19. You see, the diameter, outer diameter of our spring is to have room here, which is 10. Let's place 10. This is 10. Good. Calculate. Oh, what is this? Well, we didn't consider this. Where are the loads? 500 newtons. We need 5 newtons. Minimum load is 5. Maximum load, say 10. And working 8. Yes. Calculate again. This is no more necessary. Calculate. What you see? You see the text calculation indicates design compliance. This means is okay. Okay. Again. The name. Okay. And now we see the real spring. But when we try to move this, we don't see any change. Oh, this is not nice. Well, I tell you that Inventor, at least, cannot present a real compression of this arc. You have to accept that this is the correct spring for this, and you can buy from the shop, and it will make what you need to have. If you want to see compression, you have to use other module of Inventor, which is the dynamic simulation. We discussed about dynamic simulation. Let's create a simulation with the dynamic simulation. We create an assembly. We place a certain part, which is a disk, and another one. Okay. We constrain them to be face on the face. Yes. And to be axis on axis. Okay. And now we change the distance between them. The first, the second, not the first constraint, and we place 1, 2, 3, the distance between these two objects, identical objects. Home, they are at 1, 2, 3 distance. And now we delete this constraint, but we know that the distance is 1, 2, 3 here. Now we verify that these are still not generic. You see they are generic. Still carbon. If one is still carbon, the other is the same, because they are an object in two instances here. Now we go to environments, dynamic simulation, and we apply gravity, because we want to see how are this is grounded and this is free, to see what happens as a dynamic copy here. Vector, not entity. I have no entity to select here. Vertical entity minus gravity acceleration. Okay, the force is correctly oriented. Good. Now I make a small action here. I place these two somehow, as you can see, perspective. And now I start the dynamic simulation. Start. Pew! This is free, nothing is constraining, then it goes to the hell. Look here, to the hell. Okay. This is a point because there's 1 second here, but let me change to 10 seconds and you will see that I'm right. To the hell. And disappears. Yes, in 5 seconds is disappeared. Okay, now we constrain these two parts with a joint from dynamic simulation. The joint is spring damper jack. We select the two. You see component 1, component 2. Two components are the object. An object, not a point. Okay. Now we see a big spring here. What is this? This means that we have to edit the joint. We edit it by placing a stiffness of 3 newtons per millimeter a free length of 1, 2, 3, a radius of 12, we know the diameter of this tab, facets, you see they are rough here, we want to be thinner, 10 is the maximum facets, now it looks better. Then 11 turns, and of course a smaller wire, 1 tab. You see, this is what we have. Okay, and now what? Now if I move this, you see it looks as a spring must look. I have to wait a little. You see what happens here. Yes? Good. This is the way we can animate a spring. Using dynamic simulation, you can create a more complicated animation like this one. You see is dynamic simulation.